All right. So this is lecture 11, and today is the 1st of February. So I did send you the sample exam, which since we had discussed it, I would just set up the free body diagram again. This was a space frame or some sort of a structure which looked like this. You had a you had okay, this and C is sitting on a ball, and here there was a device that allows motion in all directions except X and uh, Z. This was X, this is Y, this was Z axis. We had a load of 900 Newton here. There was a hinge here and a hinge here, B, okay? So the free body diagram, we said, okay, here is a hinge that allows rotation. It does not allow motion in these directions. So um, these were the two unknowns. These are the two directions that the motion is restricted here. And then we had this vertical load, which is RC. Okay, so this was a free body diagram. And these direct dimensions are given 0.4, 0.4 meter, 0.4 meter here, and this was 0.4. So to start with, okay, the problem is asking you to find, okay, reaction forces at B and C only. It's not asking you even to find reaction forces at A, although you can find them, and I will do that. So you look at this problem and you say, okay, um, if I want to use the concept of summation of moments is equal to 0, which would be the best? Summation of moment about an axis or about a point? I see that if I take summation of moments about x-axis, all these unknowns intersect except are at C. So apparently this is a good axis. However, although this is a 3D problem, since these forces are parallel to z-axis that is perpendicular to xy, if I look at this frame, I'll put my eyes along x-axis, this is what I would observe, right? This is y, this is z, and this is x-axis that is coming out of this plane perpendicular to this. That is, A and B will be seeing at one point here. Now this is the x-axis. So the forces that I have, this one, the known force, and this one, the unknown that I want to find at a distance of 0.6. I want to take the moment of these about z-axis. So as you can see, the problem is reduced to a two-dimension case. That moment of this force and this force about this axis is basically finding the moment of these about point A. So that problem is quite simplified. It just comes down to what? You have the moment of this force about A, which is going to be negative 900 times 0.4 plus the moment of this about A is equal to 0. And I can quickly find this, which comes out to be 600 Newton. So you see that? Any questions? So when you have a 3D problem that forces happen to be parallel to the axes, most of the time, that problem is really reduced to a two-dimensional problem. Because the moment about this axis means what? All you need is a vertical distance from this and this from the x-axis. That's it. If you don't want to go that route and say, okay, I want to consider a position vector for this one and this one, find the moment of each, and then find the dot product of those moments with the unit vector along x, okay? Sum those up and equate those to 0, you will see you get the same equation. Because the dot product, the moment of this force with x would be the same unit vector I, which I times I gives you basically that quantity, which is this. So always consider the alternative option of considering it a 2D. Now I would say, okay, I want to find Bx and By. Now, how about if for finding Bx and By, I need to get rid of as many unknowns again as I can, right? So that with the possibility is by considering the summation of moments about y is equal to 0, or taking the moments of all these forces about A. But I will consider again moment about this axis because it makes my life easier. If I take summation of moments about this axis, right? Bx is parallel. I'm sorry, this is By. This is By. By is parallel to this y-axis. And when you have a force parallel to an axis, it does not generate a moment about that axis. In other words, think of this force. Can this force cause rotation about an axis that is parallel to it? No. That would be 0. There is no moment that this force can generate along an axis that is parallel to it. You cannot rotate something about an axis that is parallel to a force. So this doesn't generate any moment. So it's only this one, and this one. But again, to find the moment of these forces about y means that finding the product of these and the vertical distance from this axis to those, which you have. So you can see that BZ generates a moment about y-axis that would be simply BZ times its distance 0.8 and would be along that axis, right? Oh, I'm sorry. This is what I made a mistake. This is X, this is Y, this is Z. So I had this correct. So this is BX, this is BZ.
Hey,
Okay,
Professor, we can't see what you're writing up there.
oh, I'm sorry. Can you see it?
Perfect, thank
So
you.
what I said was, I need to take this one, Bx, doesn't generate a moment of X because it's parallel to it. So I only have these three. So start with the moment of BZ. BZ has a vertical distance from X, which is 0.8. So it's going to generate a moment about X, which would be this. This one has a vertical distance of 1.2, but it is also going to generate a moment of positive, and that's 1.2 times 600 I. How about, So we have this one, and this one. How about this one? It generates a moment which is in the negative direction of x, and that would be the distance 0.4. So negative 0.4 times 900I is equal to 0. So you can find BZ quickly here, and BZ comes out to be negative 450 Newton, meaning that the assumed direction for BZ was wrong. So BZ is actually acting in this direction. Okay,
Professor, I have a question.
sure.
So I actually have two. Where'd you get the 1.2 from?
For this one, for
I can't,
RC,
yeah.
yeah, this 0.4, 0.4,
Oh,
0.4.
okay, okay.
Yes.
And then
And
my other question is, how did you get it in the X direction with I hat? Like, where did that come from?
see, think of it this way. It's hard to show it. Can you see this? You're taking the moment, this is the force that you have. Let me see if I can, you see that, okay? Do you see this is the, let's say this is your x-axis, and this is the force, RC. So it rotates this way. That means it's going to be rotate this way, right? So it would be in the positive direction of x. You see what I mean? This is the line x, which is, this is the plane. This is x. Then you have this force. So, and this is the vertical distance. So what direction this force is going to rotate about x-axis using
Did you
right-hand rule?
flip the axes on the diagram? What?
You mean this is x, this is y, this is z, you mean?
Okay.
Yeah, this is the way the problem is given. X, Y, Z are given like this. So this is where parallel to Z. So it's rotating that way, so it would be along X.
Okay.
That was the confusing part. Any other questions? All right, so we found BX, I'm sorry, BZ. We found RC. The last unknown that the problem is asking is we need to find BX now, right? BX. So in order to find BX, how about now if I consider summation of moments about Z equal to 0? Because I don't want to deal with these. If I consider summation of moments about Z, all those forces that are parallel to Z cannot generate any moment. In other words, the moment of RC, BZ, and 900 about Z axis would be 0. So it's only BX, and that would rotate this way. That is going to be downward, like this would be negative BZ times this distance, 0.8 times K. But this is going to be 0. That means, I'm sorry, BX. So BX would be 0. Can you see that? Now, if you want to find AX, AY, and AZ, that's easy. You just write summation of forces along X is equal to 0. The only force you have is AX in, I'm sorry, AY in this direction. So if I write summation of forces along Y, Fy equal to 0, AY is the only force. So AY would be 0. If I write summation of forces along X equal to 0, I have AX plus BX, which I found to be 0, is equal to 0. So x is equal to 0. And then summation of forces along z is equal to 0. I have AZ, okay, minus BZ plus RC minus 900 equal to 0. RC was 600. This was 450. So I get AZ comes out to be, okay, 750 Newton negative, okay? I sent you, of course, a solution, but these forces, I just did it extra because the problem is not asking for that, but I just wanted to show you that you can also solve for those if you want. Any questions?
Is it normal to have to do 3 moment equations for a 3D problem in order to solve?
It's not normal, but you know, the concept is that you want to get rid of as many unknowns as possible. And it happens that in this case, for instance, x-axis intersect with 3 unknowns. Y-axis intersect with 5 unknowns. So I use those as the 2 equations. That's the reason I consider that. And then z-axis also intersect with 3 unknowns. So moment equal, it is normal, and I highly recommend, and that's what my advice is, that always start with summation of moments and consider summation of moments in such a way that you can get rid of as many unknowns as possible. That's the general concept or general approach. Okay.
So our strategy would be like look at the summation of moments in like about an axis or like one point, and then see if it covers everything, and then like choose a different one.
Exactly. Exactly. See if that summation, you can find a summation of moment that helps you get rid of as many unknowns as possible. That is the strategy. So with
Dr.
that,
Nair?
yes.
Yeah, sorry, quick question. So it's a little,
Sure.
sorry, just a little nitpicky. So since you switched the axes, didn't the moment about y give us the RC equals 600 newtons, and the moment about x give us the BZ?
Moment about, let's see, maybe I got confused myself. So I first, you took summation of moments about, this should be summation of moment about x, you're right.
Okay.
First I took, oh, no, sorry, no. First I took summation of moment about y,
Right.
because you get rid of all of these, right? So that will give you, okay, RC only. So that was correct, right?
Right. And then the second equation was for the moment about x.
Right. This one, then, so in other words, this was for summation of y gives you this. This one, you're right. This would be summation of moments about x is equal to 0.
Okay.
That's a good observation. Yes.
Thank you.
Yes. Yes, you're absolutely right. I'm glad you noticed it on this one.
Yeah, so it just confused me for a little bit. Thank you.
But it was a bit confusing, and even confused me because we are not used to this orientation that the problem is set up that way. So thanks for your good observation.
Thank you. Yeah, of course.
Sure. All right. So with that said, let's move on. So then, you know, as I kind of started last time, I said that in statics, we started with rigid body equilibrium, right? And I said that, and as we have seen so far, we focused on finding the external support reactions, right? So naturally, the next step is to find internal forces, okay? However, in all statics books, instead of naturally going to the next step, which is this, we take a detour and we introduce the concept of centroid and moment of inertia, or the second moment of an area. These are topics that you're not really heavily going to use in statics, but they lay out the foundation for the next courses, dynamics and the strength of material, that you will need that. Okay. I will start with centroid. What is centroid? In fact, a centroid can be very, well understood by the, referring to the very important concept that we introduced in statics, and that is the concept of equivalent systems. What is the meaning of centroid? Centroid is this. Let's say you do have an object, a 3D object. You want to locate a point, which we call that the center of gravity, where you can assume the entire weight of this object is concentrated that way. What does that mean? Conceptually, what it means is this object is made of all these tiny differential pieces. Each has its own weight, these vectors. So by finding a location where you can assume the entire weight is located, what it means is you're trying to find these distances from these two axes or locate a point where all these forces, which means their summation or their resultant, can be moved to that point, yet no moment is generated at that point. So that means you need to take the summation of the moment of each individual piece about this point equated to 0 to find these distances. That's how you find the centroid. I don't go through the mathematics of that, but in statics, you have two types of shapes or areas. First of all, we will be only dealing with two-dimensional shapes when it comes to finding a centroid. One is a shape that is given by some functions, and the other type is a shape that is made of geometric shapes for which we can easily locate their centroids. So this is the first type of problem we're going to discuss, and this is the second type. Starting with this one, which is a general shape, okay? The objective is this. We want to locate the centroid of this. That is, you want to find the location of this with respect to the y-axis, which is the distance from that. We call that x bar. And from x-axis, we call that y bar. We can show mathematically, you've seen that in calculus, you can see it in the book, that x bar is evaluated using these integral. X bar is integral of x dA over the integral of dA, y bar, the integral of y dA divided by dA. What do these mean and how do you evaluate those? Let me demonstrate that through an example problem, which is easier. I said the first type of problem that we look at are these types of problems. You have an area described by some functions. For instance, in this case, you have this function, y equal to m of x. This function, y is equal to k x squared. That intersection of these two describes this area that we want to find its centroid. This is the procedure. So I will present this problem, and of course, this is given, this distance is given as A, this distance is given as h. So first of all, you can find these constants in these functions. Since y is equal to mx, and this point A, has a coordinate that is a and h, okay? You substitute that into these functions to find these constants. For this one, you get h is equal to ma, so m would be simply h over a. And this one, you have h is equal to k, a squared, so k would be h over a squared. So the functions that you have is y is equal to h over ax, and the other one is h over a squared x squared. The procedure that I recommend is as follows. To evaluate x bar, you always set up a differential area with sides parallel to y-axis. So remember, for x, you set up a differential area with the two sides parallel to y-axis, okay? So this is dx, and the height of this differential area is what? If I call this y2, this y1, I set up dA, which is y2 minus y1 times dx. And then substitute for y1 and y2 from given these functions that you have. What is y2? Y2 is mx, which is h over ax. Y1 is this function, which is h over a squared x squared times dx. This is dA, okay? So this is the first step. The second step, you evaluate the integral of dA. So what is dA? X is going from here to here, from 0 to a. So this integral would be 0 to a of evaluating this function, which is h over ax minus h over a squared x squared dx. So the integral here is easy, is h over 2 ax squared minus h over 3 a squared x cubed from 0 to a. And if you evaluate this, you see it comes out to be what? A squared would be h. You substitute for this, so it would be h a over 2 minus substitute for this would be h a over 3. So that would give you h a over 6. Any questions?
Can I see the graph that you drew above? I didn't quite get all of it. Thank you.
Sure. So you're finding this dA, which is this distance, y2 minus y1 times dx. So that's dA, and then you evaluate dA. Okay? So now x bar, the equation for x bar was x dA divided by the integral of x dA. This you've already found is now HA over 6. So all I need is to evaluate this integral. So that would be the integral from 0 to a of x times this function, which is x times h over ax minus h over a squared x squared dx divided by HA over 6. So all I need is to perform this integration. So that would be h over a x squared minus h over a squared x cubed dx, integral of that from 0 to a divided by h over 6. So this would be if you perform the integration here, would be h over 3a x cubed minus h over 4a squared a 4 from 0, I'm sorry, x4 from 0 to a. And if you evaluate, simplify that, would be substitute for a, you get h a squared over 3 minus h a squared over 4, or would be 1/12 of h a squared divided by 1/6 h a. This cancels out with that, this cancels out with that, gives you x bar will be simply a over 2. Okay, any questions? You follow the same or similar procedure for finding y bar. For y bar, this is what you do. Okay, you look at this shape for y bar, and now you consider a differential area with size parallel to x. Remember, for x, sides parallel to y, for y, sides parallel to x. So this is dy. So dA would be this x, I call that x1, this x2. So here you set up your dA, which will be now x2 minus x1 dy. But what is x1? This was y, the equation for this was h over ax. So what is x then for this? x1 would be from this function, ay over h. Okay, how about x2? x2, this function was h over a squared x2. So what is x from here? Would be a squared y divided by h, the square root of that, or would be, okay, a y half over square root of h. So I can set up dA. Now, dA now goes from here to here. This is h. So it would be 0 to h of a y half over h 1/2, okay, minus this ay over h dy. I do not, however, evaluate this. Reason is that the integral of dA, which is what you're doing here, gives you this total area. The total area is the same. So what you did here in evaluating dA should give, if you use this approach, should give you the same answer. So I already know the answer here. Okay, so for dy, all I need to do is now set up this function, which is y dA divided by the integral of dA. And this goes from 0 to h. So what is that? Y times this, because I need a function of y here. So I have a y 3/2, okay, divided by h half minus a y squared over h, integral of this from 0 to h, dy divided by h over ha over 6. So let's evaluate that integral. That would give me a over h half divided by, that would be 2/5 of y 5/5 minus 1 over 3h, a over 3h, y cubed from 0 to h divided by h a over 6. So you get, substitute for h, for y h, so h 5/2, that means minus 1/2, that means 4/2, so h a squared, so it would be 2 a h squared divided by 5. This one, substitute, a would be h cubed over h squared, a over 3 h squared divided by h a over 6. And you simplify that, you get y bar, which comes out to be 2h over 5. And that is the y coordinate. Okay. Any questions? So that is the procedure. Okay. Very simple, right? You've had this, I'm sure, in calculus, so it's not the first time you have encountered this topic. So it should be kind of a review. All right. But let me go over yet another problem. Okay. Let's say now you have, I'm giving you another example. Let's say you have a function that looks like this. This y is given as h times 1 minus k x cubed. This is a, this is h. Okay. So let's, you know, follow the same procedure. Okay. All right. Shut this down. So what is the procedure? We start with x bar. X bar is the integral x dA over the integral of dA. I said you start with dA first. For this case, take a differential area with size parallel to y-axis. That is, this is dx, this is the height, which is from here. And by the way, you can find these this um, parameter k because you have the coordinates by substituting. For us, this is point A. Coordinates of that are A and 0. So you put it here, you have 0 is equal to h times 1 minus k a cubed. So that will give you k is equal to k h over a cube. Okay, so that's what your or actually, I'm sorry, it would be just 1 over a cube. Okay, so that's the function. So this function is h times 1 minus x cubed over a cube. So that's the function that you have. Okay, so dA would be what? dA would be h times 1 minus k, which is 1 over a cube x cubed, right? Okay, that's times dx. You follow me? Any questions? Okay. All right. So if you evaluate, now you need to integrate that from 0 to a. Okay. So if you integrate this from 0 to a, you have h times 1 minus x cubed over a cubed dx, and that'll give you what? Um, I would be just h x minus h over 4 a cubed x to the 4 from 0 to a. Substitute for those, and you will get this would be just h a minus h a divided by 4. So you get 3/4 of h a. So that is dA. Now, next step, you want to find x bar. That will be x dA divided by this integral, which you've already found, 3/4 of h a. So you only need to perform this integration from 0 to a, that is x times this, times h comes out. So that's 1 minus x cubed over a cubed dx divided by 3/4 ha. So this becomes, I take h out, and the integral of this would be 1/2, because it becomes x. So integral of x is 1/2 x squared. Okay. Integral of this would be 1/4 of x4 over a cubed. Okay. And going from 0 to a divided by 3/4 of ha. If you simplify this, okay, you will see that this comes out to be x bar. Add these up, of course. Let me first of all simplify. That would be, this would be h times 1 a squared over 2 minus, it would be, okay, this would be 1/2 x squared, this would be 1/4, so would be, also, this should be a squared somehow. Why did I end up with this? So this is 1/4, this is 1/2, and this is x cubed. So this should come out to be h over 4.
I think it should be x to the 5th over 5.
You're right, x over 5th to the 5, because this is, you're right, because I had x4, so I don't know why I wrote x4. Yes, that's right. So that's correct. Thanks for that observation. So that would be a over 4 a squared. So that will give me simply 3/10 of a squared h. So divide that by 3/4 h a, that gives me x bar 3/10 a squared h divided by 3/4 of a h. That would give me 4/10 of a. That would be x bar. Okay. Any questions? Now, if you want to find y bar, okay, y bar, you consider, this was a function, you consider a differential area parallel to x. That is, this is dy, okay? And this is the width of this rectangle, dA. So dA would be this, which is that function, h times 1 minus x cubed over a cubed times dy. Again, you don't need to evaluate this because you already have that. That is 3/4 of HA. So I only need for y bar, evaluate this y times dA divided by 3/4 of HA. And this integral y dA goes from 0 to h. And that would be the integral from 0 to h of y times h times 1 minus x cubed over a cubed, okay, dy. So we can simplify this h times this integral y times 1 minus x cubed over a cubed dy. So this becomes h would be 1/2 y squared minus 1, oops, what did I do here? No, you see that mistake I made? I should have, this was 1 minus x cubed over a cubed is equal to y. I need x. So I need to find x from here. See, that's the mistake I made. Okay? And x in this case would be a little bit complicated because you have to take this to the other side. So you have x cubed over a cube, which would be 1 minus y. So x cubed is 1 minus y over a cube, or x is this. So this is going to be the dA that I did here, I should have corrected that. dA, I should have evaluated that, but never mind, it's going to be quite a bit of work to do. So it would be the 1 minus y divided by third root of that times dy. Okay, so that's the integral that you have to do, which I did not do. Sorry about that. And so I just quit here. All right. Any questions? I was hoping to do another problem, but at least we did the X bar for that. So at least this part is correct. Forget about the Y bar. Y bar was wrong. Okay. Any questions? Okay. If not,